think so. So maybe we move to the second presentation until the first presenter arrives. Second presentation titled Numerical Simulation of Ventilation Potential in Traditional Omani House, Beit El Khanji as an example. I would like to ask the presenter to share their screen. And start presentation. Wa alaikum assalam wa rahmatullah. Please introduce yourself and start your presentation. Thank you very much.
First thing, I'm Dr. Haidar Khan, and I'm assistant professor in architecture department in SQU. And this paper is about numerical simulation of ventilation potential in traditional Omani house. We took Beit Al Khandaq as an example. So we actually work here. We are 4 doctors. We work here. I'm Dr. Haidar Khan, and I'm specialist in HVAC and CFD. There is also with me Dr. Saleh Al-Sadi, and he's more about building energy or building simulation. Dr. Naima is about vernacular architecture and building heritage. And Dr. Alia, which is about urban building energy modeling. Now, the problem here is that in Oman, we are facing a problem with the energy consumption, like 60% of the energy consumption or electricity generation is cost just for the houses. And most of this is used for running air conditioning equipment. So we find in the last years it's be better to reduce this consumption by using a passive means, and the best way to start is begin from the traditional buildings. So for this, we use this house. This is actually a picture from the house. Now, Beit Al Khandaq, it's been surveyed by the students and professors of SQU before 2 years. They did many measurements, research on it. There is a full AutoCAD drawing for the house showing every features inside it. The house is usually at 2 level, like other houses we find it in the area. And many elements, many architectural elements, you can find it similar to the region. So there is a thick walls. There are many vents, more than what we find usually in the houses in the north of Arabia, like in Iraq or in Sham. The house is rectangular with rectangular courtyard, as we see here. Here we see picture A. This is the front, and B is the gallery between the front and the rooms. Then the C is here, the courtyard. Now, the interesting thing here, as you see, there are many vents in the fronts, more than what we can find usually in the houses in other parts of the Arab world or Islamic world. So you can see those circle things are vent, the rectangular thing above it are vent. So the builder here, the traditional builder here, is try to have as much as possible opening from outside to the inside of the building. Now, this is somehow different from what we can find in Baghdad, for example, where there are few opening on the front of the house, and there is no windows, no other things. And we're going to explain it later why we have such thing. Now, the house, again, is bulky structure. So the wall usually between 70 to 40 centimeters. Not all the walls have the same dimension or same thickness. Some walls, again, it's like 40, 50 centimeters. Other maybe more thick, like 70 centimeters. Now, the rooms is longitude rooms. So the length is more than the width. And this is because the roof is supported by the trees, palm trees. So 3 meters is, most of the cases, is the width of the rooms. But the length can go any amount in parallel to the courtyard. The windows, as you see, are regulated with no glasses. However, they can close it by wooden shutters. So in case if the weather outside is harsh or there is some desert storms, they can close it by wooden shutters, but there is no glasses. Now, what we need to do here is to study the airflow in this house. The air is coming from where and move to where. And how does this affect the thermal comfort? This pictures here show the models inside. The left part of it is showing the model inside the CFD software. The CFD software we use it here is StarCCM. version 2021. And you can see the domain, the computational model in the top, when the models of the house in the down. Here in the model of a house, we need to copy every vent, every opening, we have it in actual house. So you can see in drawing E, there some rooms may has a number of vents from outside and from the courtyard side. Now, in common, the software is divide the model into number of grid. Every grid is used to solve the conversation equations. And from this, we can predict the temperature, the air flow rate, not only for the air, but also for the building structures. We use the turbulence model. We use the second order equations. And we use also to simulate the solar radiation on the walls of the building by using a solar model. We use also for the radiation surface to surface and a great thermal radiation model. Many of information, you can find it here or in the paper. The paper, also the grid here, we use polyhedral mesh, which is non-uniform and structure. We did some local refinement in some places, especially in windows, in vents, because those places are small void with a dimension much less than the dimension of the room or the courtyard. So we use a mesh there much smaller than the other places. In common, the number of a grid, it was like 20 millions, 11 millions for the domain around the house, and for the house is like around 10 millions. The model itself, it's been validated by using the research or experiments of the other. This is one example showing the drawing here, where you can see the experiment in the green, and the red is show the CFD. So there is a good agreement between the two. Now, the objective of the paper is to study what is the relation between the airflow and the thermal comfort. The thermal comfort here is used by the was predicted by using PMV method, which is a predicted mean void. And we use this method because this is the method we should use it for the research according to the ASHRAE and ISO standard. But we added something, which is the expectancy factor. And this is shown by many research. One of them is research by Fanger himself. And it's used to consider the living in building without AC, because PMV in common it's used for the AC building. So in building without AC, it's be better to use it with the adaptation effect. And adaptation effect is considered here by using the expectancy factor. So we calculate this by using a Java program and separate from the CFD software itself. And we begin the analysis for the airflow. We can see, for example, here and down left, you can see a picture for the parapet on the roof. And in the parapet of the roof, there is a many opening. You can see it's like rectangular opening down. We was curious about what it's doing actually, and we found it is more about cooling the horizontal slab or horizontal roof level, because this receives a lot of solar energy and its temperature will be increased due to that. So to cool it, they actually introduce a large amount of air from this opening, which become in touch with the level, with the roof, and this will cool it, especially in night. The effect will be much stronger. When we come to the house itself, it's showing you the drawing here on the right. And we can see how the air is come all the way from the opening, from the front, then to the room, and from the vent in the top of the wall of the room to the courtyard. And this is different from what we see in other houses in north of Arabia, where the air comes to the courtyard directly from top. Here, actually, the air comes to the courtyard through the room. So the air in the courtyard will be hotter than the air in the room because it gained the heat from the room. And for this, it would be better just to discharge it to outside rather than to take it to other rooms around the courtyard. And for this, we will see the connection between the rooms and the courtyard are so limited, and only as we see here in the right drawings or right pictures, they are just small air vent in the top of the house. And this is just a connection between the rooms and the courtyard. Now, this is different from the houses we find in Sham and in Iraq, where there is a large windows between the rooms and the courtyard. And again, this is because the courtyard is the source for the air in that case. But in this case, no, it's coming from the front of the house. Here also in these pictures, we will find the relation between the air velocity or the ventilation and the thermal comfort. So you can see here in the left drawing, where the air velocity is highest or the speed is highest, we can see the thermal comfort will be in the highest amount as well. So there are like a strong connection between the air velocity and the thermal comfort. And it's a drop in the thermal comfort here, the drop in the places with the dead airflow, as we see in the corners, in the far corners from the windows. In common, this drawing shows you the PMV, the normal PMV, and the adopted PMV produced. So in the different rooms in the ground level and first level. So you can see this is the arrangement of room, and the same arrangement we use for the ground and the first level. And it's always the first two rooms, R1 and R2, which is in the wind direction, will have the most suitable environment for the humans, because the low number shows that the weather there is cold. The highest number shows the weather or the environment, sorry, inside those rooms are warm or even hot. So over 2, it's actually hot. Under 2 to 1, it's warm. And you can see if we use PMV, most of the rooms, except the first 2 rooms, it will be within the warm, so it's outside the thermal comfort. But if we use the PMV reduce or the adopted effect, we can see most of the room are actually within 1 to 0, which is within suitable level for the thermal comfort. However, some rooms without windows will have, even with the adopted effect, will have a higher than acceptable level of temperature or thermal comfort, as in room R3. This is actually a room without windows. You can see it here. The level of the thermal comfort of PMV numbers will be too high in comparison with the other rooms. Now, this drawing will compare the 4 cases, or 3 cases for the opening. There are cases all the doors, all the windows are keep open. We have another case, this is in orange, where we close the doors, and in gray, we close the doors and windows. So you can see it's always at the front or in the wind direction, the PMV or the thermal comfort level are somehow within acceptable level, especially with the all opening and door close. But if we close everything, then it will be over the thermal comfort or acceptable thermal comfort level. In the rooms like FR8, this is room in the downstream, and it will take some air from the courtyard. This air will be hotter than the average. So we can see the thermal comfort is go over the acceptable level. Here, we assume the outdoor air is colder than the indoor air, because in Oman, we have sometime during the day where the air temperature will be relatively colder than the average. Now, the study concludes at the end that we need airflow to provide indoor thermal comfort, and this is the main mechanism they use it to provide thermal comfort in traditional houses. They use shading, but in this degree. Therefore, the airflow is better generated when more window exists on the external parameters than the internal ones. So it's somehow different from other houses or courtyard houses like in North Arabia. The thermal comfort can vary with the room location. The thermal condition in the house core are more dependent on the room than the outdoor air. And there are many other building elements in other houses that could be studied in the future. We will find other elements that need to be studied, but we didn't have enough time and enough space in this paper. So this is all. Thank you. And if you have anything, please put it in the question.
Thank you very much, Dr. Haidar, and thank you for keeping the time. Excellent timing. Could you please stop sharing, Dr. Haidar? Thank you very much.
Wait a minute.
Do we have the presenter for paper number 40, titled Numerical Simulation of Indoor Ventilation Designed to Promote Comfort? I cannot see names of any author of that paper. So we'll move to the next paper, paper number 56, titled The Impact of Olfactory and Airflow in Street Market. So I'd like to ask the presenter to share their screen and introduce themselves and start the presentation, please.
Good morning, everyone. Can you hear me?
Perfect. We can see and hear. Go ahead, please.
Great. I'm Nohab Bessi. I'm a PhD candidate in Cairo University in Egypt. Today, I'll be presenting the impact of olfactory and airflow in open street markets. Recently, street markets has become a target destination venue for leisure since the COVID-19 pandemic in 2020 and escape from indoor spaces. In New Cairo, Souq al-Rahab, an open street market, maintained its liveliness with high intensity usage since the pandemic due to the variety of services and daily commodities it offers. The masking and unmasking of notice due to COVID drew people's attention to the significance of the sense of smell and sensory research on perceiving the environment impacts highly people behavior. However, previous research discussed the olfactory of cities as part of the city image, and the literature is really scarce and lacking. Research on olfactory is as important as visual and auditory analysis. This paper is actually a part of a PhD dissertation in urban design studies at Cairo University. There are a lot of limitations when it comes to study the olfactory in urban studies. And we try to overcome this limitation by designing a new methodology to link the qualitative analytical part of the olfactory and link to a more measurable aspect, which is also related to the human senses. Thermal comfort, which is also a sensory research. Both thermal comfort and olfactory is highly impacted by the airflow, and thermal comfort affects the perception and performance of individual, which leads to affecting humans' behavior within the environment. We're trying to answer this question of how can we use the olfactory and thermal comfort to improve the usability of outdoor street markets. We used this methodology, which was basically divided into two tracks. The first was the field work. A smell mapping experiment was designed to map the olfactory of Souq al-Rahab. Basically, we were trying to extract the likeness, the memory triggers, and the expectations that the olfactory caused and how it impacted the perception. And we run computer simulations, microclimatic simulations on 3 wind speeds to extract the PET value that represents the thermal comfort, try to correlate both perceptions from both methods to find the right answers. Well, to smell Souq al-Rahab, I'd like to give just a brief background. Souq al-Rahab is located within the gated community, within a gated community of Rahab town. It's actually, Souq al-Rahab is located on the periphery of this, let's call it town. And the town is located in New Cairo, which is on the outskirts of Cairo. You can see here this red, I don't know if you can see my cursor. Oh, there it is. You can see here this red frame is the area that is under study in this paper. If we zoom in more, this is the middle area here is the one under study, which has an agglomeration of food enterprises. And this is the key of usually how people behave within the space. When we refer to walking, it's not just walking, it's also buying commodities, eating, interacting. Well, the smell map experiment was actually made out of 11 participants, and it was designed that each participant would stop at these 19 stops that is located on both maps to try to extract how they felt, what it triggered the olfactory when they focus on the sense of smell. The key for both maps, like the land use map on the right, is actually extracted through a pilot study done before starting the smell walking method. On the right, smell map show the collective smells of smell walks in the 19 stops. Sorry, it's on the left, not on the right. And on the right, land use map, according to the food categories they produce, extracted from the smell walks. Actually, unexpected memories were written, varying in which some were people related to place related. Memories written were mainly related to childhood memories, favorite activities, family and friends gatherings. And memories and comments are related to participants' cultural backgrounds of countries they were raised in or lived in for significant periods in their lives. They all had Middle Eastern backgrounds, but some of them lived abroad. The olfactory is in the zoo gives a sense of nostalgia to most of them that is cultural specific. All descriptions of the smells and place related to smells were related to the Middle Eastern background they had. The perception of participants, thus their behavior after the smell walks changed from being observant and alert to the sense of smell into more curious to buy, eat, or drink in the zoo. The correlation of the smell mapping and thermal conflict, as you see, we chose here to focus on, we're actually looking for spots of high satisfactory for the users within the market. On the left, smell maps of stops with high likeness correlated with wind flow extracted from the thermal maps. We had a lot of thermal maps because we run simulations on 3 different wind speeds to extract the PET value. And on the right, it's a micro climatic analysis. This is only a sample of all the maps, all the simulations that were run. This was done at 7 p.m. The main aim of the correlation is to look for spots with high satisfactory, as I mentioned earlier, in respect to the olfactory analysis and microclimatic analysis. Market olfactory is a memory trigger of places and people. Memories are culturally influenced. And it showed that the olfactory adds to the user perception of the zoo being more than just a food or commodity outlet. It influenced on behaviors that was evident during and after the experiment is over. Land use distribution of food shops had influenced the olfactory parameter in the zoo significantly. Results from the smell maps revealed that the type and number of smells at each space depended mainly on the airflow articulated by the urban environment. According to the thermal sensation votes and comfort levels, the participants had high tolerance to heat, and wind is directly proportional to thermal sensation, where higher wind speed improved the comfort levels across the different spaces. High wind speeds improved the thermal sensation significantly at 9 p.m. compared to earlier simulation runs. We had 3 simulation runs at 5 p.m., at 7 p.m., at 9 p.m. We chose those in correlation with the smell walks done at the same periods of time, which we chose also these time slots because it was very intense and the intensity was very high with usage in the market at these times of the day. Microclimatic simulation with various wind speeds played major role on the type and number of smells at each space, which influence people's satisfaction and perception at these spaces. The aim was actually to design, the main aim here is to design street markets with better users experience adding to the leisure aspect. And while considering the 2 main senses, thermal sensation and sense of smell, both crucial senses for the human perception, thus their behavior. This paper relates the olfactory smells to conclude. This paper relates the olfactory smells to the factory memory and expectation to generate a user's perception to the spaces, which helps design street markets with better experience, adding to the leisure aspect. methodology designed for the paper could be reused in other markets, and we actually are doing that right now. This paper is a part of a bigger study that compared different scenarios to improve the built environment by adding vegetation or wind barriers that could also articulate the olfactory within the market, thus providing a better experience and urban perception for users. It's, as mentioned earlier, it's a part of a PhD dissertation, trying to relate the olfactory as a crucial parameter in adding to the image of the city and the sensory research that influence the perception of places. Thank you very much.
Thank you very much, Noha, for the presentation, and we wish you all the best in your PhD studies. Hope to see you with the DR very soon. We have good time, so we'll move to the next presentation, paper number 78, titled A Cross-Scale Field Study on the Role of Natural Ventilation in Adopt Urban Heritage Buildings. So I'd like to ask the presenter to share their screen and introduce themselves and start the presentation, please.
Yes, hello, I'm Stavroula Travalou. I'm not sure if you want to proceed with the first paper. I can present number 78, but the presenters of the first paper are also here. So should I proceed or?
I think you go for this. We go for this presentation, and the presenters of first paper will follow, inshallah.
Okay, so let me share my screen. Okay, so just a little bit. Can you share my screen, the full screen?
Yes.
Yes.
Yes. Go ahead. Thank you.
So thank you very much for the very interesting presentation so far. I'm Stavroula Travalou, researcher in the University of Cyprus, and I will present the cross-scale field study in urban heritage adopt buildings. So starting with a short introduction, prime cooling mechanisms of natural ventilation are associated with the provision of a higher indoor airspeed and nocturnal convective cooling, which is particularly effective in climates with large diurnal temperature variation and buildings with high thermal mass. Besides the building layout, the cooling effectiveness of ventilation is highly determined by both urban scale attributes such as urban density and street canyon geometry, and also occupant behavior. These two aspects are further investigated in this study through a cross-scale approach. Occupant behavior, as well as indoor and outdoor environmental conditions, were monitored in the historic center of Nicosia in Cyprus. Specifically, 3 heavyweight buildings were selected for environmental monitoring located in 3 urban canyons with the same orientation in 2 characteristic areas. The focus is on 2 characteristic elements of vernacular architecture in the Mediterranean and across the Balkans. The central pass-through space portico, which is the central part here of a 3-bay arrangement building that connects the street with the courtyard, and the timber projecting volume with multiple windows, which is usually located in the first floor of the building, right here. So the cross-scale nature of ventilation is addressed in this paper through field measurements in the interior of a typical adobe building, the street canyon, and the reference height, which is approximately 2.5 times the mean height of each neighborhood. Area 1 lies on the west part of the walled city, as you can see here, and is mainly comprised by 2-story buildings, and area 2 is covered by ground floor residences with large courtyards settled in a more organic and irregular street pattern located on the east. There is a set of morphometric variables that were adopted in each scale. In neighborhood level, these are the sky view factor, frontal and planar packing density, mean building height, and Street canyon level, the morphometric variables concern the orientation, the aspect ratio, and the sky view factor. And here you can see the monitoring location in each street canyon, which is the mid-height in the two narrow canyons that were selected, and the rooftop level in the square cavity canyon in area 2. 3 buildings, sorry. So 3 case study buildings with tripartite arrangement and portico spaces were selected. Specifically, building BO2 has the Sahnisi projecting volume, is located in area 1. Building BO2 is a double-story building with portico, also located in area 1. And B3 is a single-story building located in area 2. A comparative analysis of the morphometric variables that describe building geometry indicate that building BO2 with the Sahnisi is more compact than the others, with compactness ratio higher than the other buildings. And similar window to wall and window to floor ratios were noted, whereas the porticos of building BO3 and B4 are the ceiling height are greater and around 1.5 the ratio. Indoor and outdoor environmental monitoring were monitored through relevant equipment for various weeks. The first part of the monitoring period involved the unobstructed operation of windows by the occupants, and in the second part, occupants were asked to isolate the portico space and apply all-day ventilation with a maximum percentage of window opening. The aim of this experiment was to identify the maximum indoor air velocity in each building. 3 adaptive thermal comfort standards applicable to mixed mode buildings were used comparatively for the assessment of thermal comfort. It is interesting to note here that the lower limit of the examined standards are similar, allowing for lower temperatures and nighttime ventilation. It is also evident that the comfort zone prescribed by the European comfort standard EN 16798 has a greater tolerance and allows for a greater peak indoor operative temperatures compared to SRI 55 and the mixed mode model of Barbadilla. So passing on to the results, when occupants were freely operating the envelopes openings according to their needs and habits, the ground floor portico of building BO2, the one with the Sahnisi, was operated in single ventilation mode with partial opening of just the door towards the courtyard, which is here. The first floor portico was operated in cross ventilation mode from 7 o'clock in the morning until the 9 o'clock and around 9 o'clock in the morning, with wide openings of the Sahnisi's windows and the windows toward the courtyard. While there was no ventilation during from 10 until 7 o'clock in the afternoon. Finally, during the night, shutters were applied in the Sahnisi window for safety reasons. This multi-stages window opening behavior obtained very good results in terms of indoor thermal comfort. As you may see here, the percentage of time within comfort in the ground floor portico ranged between 94 and 100%, and in the first floor portico between 63 and 97% according to the thermal comfort standard applied. During the maximum ventilation experiment, a higher window to floor ratio was established in the ground floor portico, and cross ventilation was applied in the first floor portico during daytime. So you can see here during daytime there was a cross ventilation in the first floor. With wide opening of the Sahnisi's windows. Although the applied window operation pattern was driven by the aim of recording the maximum indoor air velocity rather than obtaining indoor thermal comfort, it is interesting to note the impact of excessive daytime heat gains in thermal comfort assessment. As observed, the As observed, the percentages of time within comfort in the first floor portico were reduced to 80% according to the European standard, 42% according to ASRA 55, and 39% according to the mixed mode model. Peak indoor temperature in the ground floor, which is the dark line you can see, dark green light you can see here, remained 6 degrees lower than the peak canyon temperature, whereas in the first floor portico it remained just 1.5 degrees lower than the canyon. Air velocity in the first floor portico during cross ventilation mode remained higher than 0.2 meter per second and reached up to 0.6 meter per second during the afternoon. Occupants of the single-story building B3 were keeping the embedded openings of the main entrance door, which are these openings right here in the door, on the door. They were keeping them partly open throughout the day and the night. The transom window on the upper part of the door was always closed due to difficulty access. Cross ventilation was occasionally applied from 5 in the afternoon until 11 in the night by opening the door towards the courtyard. The obtained percentages of comfort for this window opening pattern were quite low, ranging from 20% to 67%. During the ventilation experiment, there was a partial opening of both the door of the upper window towards the courtyard, this part here, during the daytime, allowing for buoyancy-driven ventilation. Despite raising daytime ventilation and heat gains, this opening pattern significantly raised the nighttime ventilation rate, and the overall performance was improved. The percentages of time within comfort were adjusted to 57 to 81% according to the standard assessed. Peak indoor temperature remained approximately 3 degrees lower than the peak canyon temperature, and nighttime temperatures were approximately 5 degrees higher than the outdoor environment. Air velocity reached 0.2 meters per second in the early afternoon and up to 0.4 when during the afternoon, when the reference height, when the wind speed at the reference height is at the maximum potential. Moving on to building B04, occupants were applying all-day ventilation. The door towards the courtyard in the ground floor portico was partly open, and the embedded windows and the door of the entrance, these ones here, were only sporadically open from 6 in the afternoon until 10 in the night. The first floor portico was operated in cross ventilation mode, yet the upper windows towards the veranda were closed. The particular pattern resulted in a very poor performance, with a percentage of comfort ranging from 30% to 54% for the ground floor portico and 9 to 39% for the first floor portico. It should be noted, though, that the additional room that was constructed in the courtyard during renovation, which is highlighted here, interferes with the portico's cross arrangement of the windows, which is no longer straightforward. So the courtyard door is not aligned with the entrance door of the portico, while the role of the courtyard is also diminished as vegetation was removed. Also, the occupants had just moved into the dwelling and had no experience living in a building with high thermal mass. During the ventilation experiment, ventilation rate was significantly increased. The door towards the courtyard was widely open throughout the day and night, and the embedded windows were also partly open during the daytime. In the first floor portico, the upper windows towards the veranda were partly open, which enabled for buoyancy-driven ventilation. So this greater ventilation rate during the night, along with the combined effect of buoyancy-driven ventilation, has brought an improvement in the percentage of time within comfort, which ranked in significantly better levels. Temperature in the ground floor portico, the dark blue, the dark purple line here you can see, was 3 degrees lower than the canyon temperature in the first floor portico and just 1.8 degrees lower than the canyon temperature. Air movement in the ground floor portico remained at minimum levels, as you can see here, whereas in the first floor portico, it reached up to 0.4 meters per second during the daytime. Now, regarding the cross-scale airflow gradient, outdoor measurements indicated that the prime wind direction is west-southwest. The wind is strongest in the early afternoon and substantially weaker during the night. In Area 1, the mean wind speed recorded at the reference station, A1, was 3 meters per second, whereas in Area 2, it was 1.5 meters per second. And this is justified due to the difference in the reference height. The mean building height in Area 1 is higher, so is the reference height in station A1. Also, in Area 2 is located downstream to the main wind direction, and therefore it is affected more by the drag force of the upstream neighborhoods. Wind velocity in the street canyons is found to be approximately 1/3 of the reference wind velocity. So this ratio of the reference to the canyon air velocity. In the portico spaces, there was no air movement recorded for the majority of time. And actually the percentage of air velocity above the accuracy threshold of the equipment, which was 0.1 meter per second, was less than 10% and was recorded in the early afternoon. An exception is the first floor portico of the building that incorporates the element of the Sachnisi and recorded air velocities, significant air velocities for approximately 20% of the time. So in general, the first floor porticos recorded higher air velocities than the ground floor porticos, and it was found that the peak indoor air movement reached up to 1/5 of the canyon's wind speed. In conclusion, this study focused on the environmental performance of adobe buildings with pass-through spaces porticos located in dense and organically developed urban centers. Wind velocity in the street canyons was found to be approximately 1/3 of the reference wind velocity, while peak indoor air movement reached up to 1/5 of the canyon's wind speed. This provides very limited potential for cooling ventilation, as very low air movement of up to 0.1 meter per second was recorded during early afternoon in the porticos for just a few hours, when reference wind speed is at the maximum potential and is perpendicular to the canyon axis. The portico space with the Sachnisi is an exception, as it presented the highest air velocity, up to 0.6 meters per second for the longest period. Reflecting on the observed occupant behavior, several key points were raised. Firstly, safety is a major concern for occupants, hindering the application of night ventilation. Secondly, while vernacular dwellings provide the opportunity for buoyancy-driven ventilation, upper windows are difficult to access, thus they tend to remain closed. Regarding the level of awareness, in some cases, occupants seem to be aware of the way thermal mass works, maintaining greater ventilation rates at night and obtaining thermal comforts for most of the time. Yet in other cases, occupants seem to ignore an apt window operation pattern or are unable to apply such due to practical reasons, for example, their occupancy schedule, safety, difficulty in assessing the upper windows. Alterations in the building layout, the arrangement of the windows, and the role of the courtyard are also reasons for halting the potential of natural ventilation. Consequently, the dissemination of passive design strategies employed by vernacular architecture is crucial not only to occupants, but also to professionals working in the field of conservation. Thank you very much.
Thank you very much for the presentation. I would like to remind the audience to type in their questions in the question and answer box, please. We move now to paper number 40, a numerical simulation of indoor ventilation design to promote comfort. I would like to ask the author to share their screen, introduce themselves, and start the presentation, please.
Okay, you can see my presentation?
Perfect. We can see and we can hear. Could you please put it in full
Okay.
screen?
Thank you very much for your attention. So,
Just put it in full screen, please. Yes, perfect. Go ahead.
okay. So my name is Eusébio Conceição, and I will present this work entitled Numerical Simulation of Indoor Ventilation Designed to Promote Comfort. The work is developed in the University of Algarve with collaboration of the University of Reading. So the main objectives are the first one is the application of horizontal confluent jet ventilations in the experimental chamber. However, in this paper, only I show some numerical results. I intend to calculate the thermal comfort, indoor comfort, and drug risk that the occupant are subject, and also evaluate the heat ventilation air condition performance using the air distribution index and the air distribution turbulence index. The numerical simulations developed use three kinds of models. Is a coupling of three numerical models. The first one is the building thermal behavior that simulates the whole building temperature and use the inputs in the CFD and human thermal response. The CFD simulates the airflow inside the space and around the occupants. And the human thermal response evaluate the thermal comfort and the local thermal discomfort. This is some pictures about the human thermal comfort. That is the main important to evaluate the thermal comfort that the occupant is subject. So the human body in this case is divided sorry, in 35 elements. Each elements is divided in core, muscle, fat, and skins, and each one divided in several layers. For example, the skin, consider the cold and the arm thermoreceptors. It's very important to evaluate the local thermal discomfort. This picture shows the arterial and venous capillary systems that is simulated in numerical human. And this picture shows the closing thermal systems. All human body sections is protected from different slices. Each slices is composed with the outer clothing, hair, and other components. The more important is the heat exchange between the human body and surrounding environment. The numerical simulation considers the respiration, evaporation, conduction, convection, and radiation. The radiation is a very complex part and is divided into parts. Direct solar radiations that the human body has subjects, and heat exchange between the human body and surrounding surfaces by radiations. In the two cases, the shading devices that all human body sections are considered, and the surrounding surfaces is considered in these numerical simulations. So, in order to evaluate the heat ventilation air condition performance, is used an index, air distribution index. This index considers two parts, thermal comfort number and air quality number. The first one considers the effectiveness for air removal and the predict percentage of dissatisfied peoples that is used to evaluate the thermal comfort. In the indoor air quality number, consider the effectiveness for contaminant removal and carbon dioxide concentration in the respiration area that is used to evaluate the indoor air quality. I use another index, air distribution turbulent index. It's similar from the previous, however, consider the drug risks. The drug risk is very important in ventilated spaces. So in this case, the ADI number, consider the thermal comfort number, indoor air quality number, and the drug risk number. the first two, it's equal to Previal index. However, the drug risk numbers depends on the effectiveness for airflow removal and the drug risks, because it's very important ventilation spaces. In order to evaluate the thermal comfort, the human body consider the heat exchange between the human body and surrounding, and depends the air velocity, mean radiant temperature, relative humidity, air temperature, activity level, and clothing level. In order to evaluate the thermal comfort, I use 3 categories present in the ISO standard and ASHRAE. So in this case, I consider the category C, that the predict percentage of dissatisfied people are lower than 15%, and the predict mean what change between minus 0.7 to 0.7. In order to guarantee the simulations, is necessary to implement a grid generation. Here you can see the grid generation used in the human thermal response. And after, I will show the grid generation using in the CFD. In this case, I use box. In the previous, I use cylindrics and sphere. So the numerical simulations, I consider a confluent jet ventilation system with an inlet system and exhaust system. But systems are located around the occupants. The exhaust systems is located in the one duct located above the heat level in the central office area. Inlet systems based in 4 ducts and located in all corners promote horizontal descendant near the wall and the floor. I simulate 4 categories, category A, B, and C. Here in the paper, you can see the input values. And this is a typical cold simulation in winter conditions. And the main idea is to guarantee internal conditions and mean internal condition for the air temperature around 20 degrees. Here you can see the pictures with the CFD simulations. The first pictures show the CFD, and the other pictures show the human thermal response. So you can see it's the typical climate chamber of input systems. They are inlet systems is located near the corridor and near the floor level, and the exhaust systems in the middle of the experimental chamber. The chamber is occupied for 4 students, and now I will show more details about the numerical simulations. This picture, you can see the air distribution velocity around the occupants for the case A, B, C, and D, and you can verify that the air velocity is higher near the floor level and increase when the airflow increases. After, I will show the temperature distribution around the occupants, and you can verify that in general, the air temperature is quite constant. However, the upper sections, they present higher temperatures. These pictures show the drug risks that the occupants are subjects. The drug risks is higher in lower human body sections and increase when the airflow increase. However, these pictures show that the drug risks are in accordance with the international standard. These pictures show the thermal comfort number, air quality number, drug risk number, air distribution index, and the air turbulent distribution index. So for the case A, B, and C, and you can verify the thermal comfort in general decreasing when the air velocity, airflow increase, the air quality increase and after decrease, the drug risks decrease, and then air distribution and the ADI and the DTI decrease when the airflow increase. However, the air distribution index is higher than the air diffusion index because the last index, ADTI, consider the drug risks. And the drug risk is a very important parameter. Also, the air quality and the thermal comfort. So you can verify that the thermal comfort are in accordance with international standards for the 4 case. However, the carbon dioxide concentration that is associated to the indoor air quality is not acceptable. However, it's near the acceptable values. So in conclusions, in general, the air velocity and air temperature around the low body sections are higher than in upper body section. The drug risks around the occupant's body section increase when the air velocity increases. In general, the drug risks in the lower body section is higher than the upper body section, and the drug risk level is acceptable. The predicted percentage of dissatisfied peoples that is used to evaluate the thermal comfort, and the carbon dioxide concentration that is used to evaluate the indoor air quality decrease when the inlet air velocity increase. The thermal comfort is acceptable. The indoor air quality is near the acceptable values. The thermal comfort number decrease when the inlet air velocity increase. The indoor air quality number increase from the case A to B and decrease from the case B to D. The drug risks number decrease when the inlet air velocity increase. Thus, the ADI and the ADTI values increase from the case A to B and decrease from the case B to C. However, the ADI value is lower than the ADTI. So I suggest use the ADTI to evaluate the 8 ventilation air conditioning systems in this case. So in the further results obtained, I verify that the higher ADI and ADTI and air quality number values is verified for the case B. So I suggest in this case to use the case B conditions in the order to guarantee thermal comfort for the occupants and the air quality and thermal comfort. So in future, I will use this kind of philosophy to an auditorium. I will introduce the occupants, the ventilation systems, and I will evaluate the thermal comfort, local discomfort, and drug risks that the occupant is subject. Thank you very much for your attention.
Thank you very much for the presentation, and I'm glad that you made it to the presentation and we covered all the papers that we have on this session. Dr. Madavi, do you want to handle the question and answer session? We have 10 minutes for that, or 9 minutes.
Thank you very much.
Thank you.
Are there any questions? I saw one question that Dr. Haider has answered. So I think there are no questions further on from the audience. Attendees, do you have any questions? You can type in. Otherwise, I have written down just 2 questions to Professor Haider and the other student, PhD student. First, I'll ask the question to Professor Haider. It's a wonderful presentation and a great study of Baidal Khandak house, a traditional house in Oman. I'm just curious to know if there are any users living in the house at present. Are there any people living there?
Sorry, can I answer?
Yeah, please, Professor Haider.
Okay, actually, we put the temperature inside the house higher than the outdoor temperature and within the temperature of the human body. So the initial temperature of the air inside the room, it was 36 to 37. When the temperature outside is colder. So we somehow simulate the existence of the people inside the house.
Oh, okay. And my next question is, how do interior details such as blinds or furniture arrangement affect the thermal comfort? Have you studied that?
No, because the house already use simple furniture. So they are not that big bars like what we have in modern houses these days. So we didn't simulate it that much.
And the blinds and curtains, in the olden days also had fabric curtains.
They don't use. So they just put the windows and there is like a wooden shutters. That is it. So there is
they
no
they don't want-
curtains.
Okay. So there is nobody who's living in this house now.
Now there is people living in it, but the problem nowadays, they put actually AC units in the house. So if I'm doing a practical measurements, it will be for not a passive cooling, but for active cooling.
Ah, okay, that's very unfortunate.
Yeah.
Thank you so much, Professor.
Thank
Wonderful.
you.
I have another question to Miss Noha. You have, are you there, Miss Noha?
Yes, I can hear you.
So I think that's a wonderful technique and a beautiful device to map the smells in a market, in a souk. So question number one, is it a traditional souk or is a modern area? Question number one.
Yeah, actually, no, it's not a traditional zoo. It's a modern area in a new city, because New Cairo is on the outskirts of Cairo. I don't call it a suburb. It's more of a city, a new city. And it's actually located within a gated community, the Rahab town, which is run by a mega, what do we call it? A mega investor or a mega developer.
So the next question, it's a subsequent question to that. Did the smell change during the day, and did it change seasonally?
It changed during the day according to the intensity of usage, because the area that's under study is basically made out of a lot of food shops there, food enterprises with different backgrounds, Syrian, Egyptian, Lebanese. And during morning hours, there are some usage, but it's not very high. And during the afternoon, starting 4 to 5 p.m., it becomes really crowded at times. During the year, the intensity is similar. Even during winter, people still go there, especially during the pandemic, because it's an open street market. However, it might differ that the souk is less intense in winter during 9 o'clock, because people in the cold weather would like to go home earlier. Did that answer your question?
Thank you. Yes, wonderfully. Yes. Did the smell patterns change seasonally? Because in the season, with the seasonal shift, there would be wind moving.
Yes, but not because of the wind change. The prevailing wind is usually the same during the seasons, but because of the fruit season. Sometimes we had, during our investigation, we had the mango season in Egypt. Mango has a highly prevailing smell, and it's a very strong inducer of memories in Egyptians, because it's all related to summer times and family gatherings. It's a very important fruit, and it's only present during 3 months of the summer season. However, in winter, it will not be there. Other smells might pop out. Also, before the pandemic, there was the shisha tradition within this market. Most people go there to have shisha. The smoking traditional smoking device that people use on cafes. But since the pandemic, it was banned, and I had some participants who visualized it, who actually felt the smell there only because they felt they were trying to pay attention to their sense of smell. They're expecting to see or smell shisha, although it wasn't there. And I kept telling them, no, okay, write it down if you can smell it. And they can smell something that's not there only because they feel it should be there. So on normal occasions, post-pandemic, there was something prevailing smells of shisha, but now they're not there, and they're still felt or expected.
Very nice. That's really, smell memory, olfactory memories, they're drawing back.
Exactly, yeah.
Interesting. That's really, really interesting. And this similarly, people also have thermal memories. So they visualize visiting Alps or, visiting desert safaris. And
exactly. The fact that it's not a traditional souk, but it's trying to imitate a traditional souk. And as I said earlier, it's a part of my dissertation the coming case study should be a traditional soup. So yeah, it's a very good question. Thank you for asking it.
Thank you. Any other questions from other presenters or the attendees? I see there are 13 attendees. If you have any questions, do type in and we would be able to ask them. Yeah. Any questions?
I have a question if no one else
Yeah.
has.
Jahan.
Actually, I have a question for Dr. Haider and another for Nuha as well. So I'm following your step, Dr. Madavi. Dr. Haider, how important Beit al-Khanji is from heritage point of view? How significantly it represents the traditional Omani houses? Because the picture you showed us, it shows like a house of a rich family that are not very common in Omani tradition. Is this can be considered as a typical Omani house and lessons can be drawn from that particular house?
First, we don't have a typical Omani house. We have a number of typical houses. So with the regions, the houses are different, and with the economy income, also the houses are different. Now, we use Beit al-Khandaq because the structure, it was safe and it's good to work with it. There is other houses are more typical, but we couldn't find anything remaining from it to draw it or to work with it. So for this, we work with what we have. But in common, it can give a good example for the houses in that region.
Perfect. Perfect. Thank you very much, Dr. Haider, for the
Thank you.
clarification. Thank you. My question to Nuha. Nuha, you studied the olfactory aspects in a gated community, which is a Rihab, as you mentioned, in Cairo. My question is, we all agree of the importance of senses in urban design and architecture. And I can see how important what you are doing is. However, don't you think that Egypt and Cairo in particular has more important aspects to deal with from urban design point of view? My question is what's the motivation behind studying this particular aspect in a gated community?
Well, it's the COVID, actually.
Good, fair answer.
Yeah, honestly, my sense of smell is, I've always had a very strong sense of smell, and I've never paid attention of how important that was until I lost it when I got the COVID. And how during COVID, during the lockdown, all souks were locked, all streets were silent, we could smell nothing, but surprisingly, Souq al-Rahab was working. And it has some political aspects to it, I guess, but it was working and it was alive. And it was, let's call it a fresh breath air to go there and smell food, actually, when everything else was locked down. And that was the main motivator for me to start from there. And I had a lot of doubts about studying this souq because it's a new souq. It's not a traditional one. It doesn't have historical significance, but it has cultural significance because it's actually a very good presenter of the different cultures that accumulated in the previous years in Egypt since 2011. Because we have a lot of Syrians inhabiting Rahab. We have a lot of Iraqis. We have a lot of Lebanese. We have a lot of Egyptians, naturally, because we are in Egypt. And they all come together in this souq with a different food, and they just live their life. I just chose a very simple aspect because it's highly understudied, but it's highly influential. There was a lot of inspirations that people kept commenting on. I smell shawarma, I smell mango, I smell, and all this came before I even thought of studying the olfactory. But I just thought to bring it on since it's more of a cultural, how do we call it, multidisciplinary souq, and use it as a pilot for other studies later on.
Thank you very much. It's actually enlightening how the pandemic did actually attract our attention to things that we thought it's not important, but nowadays we're looking at what's normal in a different way. So thank you very much for the answer.
Thank you. Thank you for asking.
Any further questions from other presenters? I have written down a question for Dr. Tarawalo. Yes. See, you have shown, are you there, Dr. Stravola?
Yes, yes, I can hear you.
So my question is between, you have shown measurements of houses that have double pitched roof and single pitched roofs. So is there any difference in indoor air velocity between these two? Houses that have slope on both the sides and houses that have slope only on one side?
The traditional roofing is mainly double, the double slope. They have the double, it's a pitched roof. You have seen in the section the one that had one, just one slope, yes, one pitch. But the rule is that they have both slopes. So we're talking about an urban center, mainly comprising with this type of roofs. And there are certain cases with single pitch or flat roof, because they might be new buildings, you know, in an urban center. This is something that is very organic and it's not fully protected, all the buildings. So new buildings may also arise. So the whole study demonstrates how in real urban centers, in historic urban centers, how the flow is so complex and it's attributed to many different aspects. So we cannot isolate one parameter from the other. If we wanted to just study the role of the slope, then we would have to practically move to numerical studies or laboratory studies with models. But in real field conditions, this is very difficult to attribute the results to one particular aspect.
Okay, okay. Thank you.
Dr. Madavi, I think we need to close now because other session has to start, so we need to wrap up the session, please.
Thank you very much, all the presenters, Dr. Ilham and other speakers. It's been a wonderful session. See you again, hopefully in next CATE in person. Thank you very much.
Thank you very much. Next thing, we have the keynote speaker at 1:10.
Yes.
The link is on the program. See you all. Thank you very much. Bye-bye.